Hello, welcome back. It's Infinite Series today. Yesterday we did sequences, and now we're into series where we're taking these sequences and we add them up. So previously we played around with sequences, and we're mainly interested in what the end behavior was as n approached infinity. Did these actually converge to a number, or did they diverge? We take this a step further by performing a mathematical function on these sequences. In this case, we're going to be adding them to turn a sequence into a series. And so we have these the sequences as we add more terms into it, as n goes from 1, 2, 3, 4, they actually are summed up. In this example here, we take 1 plus 1/2 plus 1/4 and continue onward. So it's basically the sequences of 1 over 2 to the n minus 1. And as you add more terms, you get this, in this case, it will converge. In fact, it will converge to the number 2, because it's 1 plus 1/2 plus 1/4, and eventually you'll get very, very close to 2. It doesn't always happen that they converge. Sometimes they actually diverge and don't approach any number at all. And so on these, they have the instantaneous value as you add terms, such as the first one is 1, and then you have 3/2, 7/4, so on like that. And if you wish, you could create a function for that. These can be sort of difficult to do. And then you have this rule for the partial sum, which can be a little bit tricky to do as well. And what you see here in this denominator is, as n becomes large, the denominator is going to be very small. Eventually, this all will reduce to 0, and the answer will converge to 2. So that's the idea of what the introductory to what this is about. Throughout Chapter 10, you'll see some much more sophisticated examples than this, but we'll work you up to that before we get there. So we can predict if these sums converge to a fixed number or diverge to infinity. So an infinite series is a summation of an infinite number of terms. A of 1, A of 2, A of 3, added in forever, basically. And on your way to this forever, you'll have this sequence of partial sums that are instantaneous sums for wherever you're at in your summation. And so if these partial sums converge to a number L, then the series converges. And the sum of that series for all numbers for all positive numbers up through infinity is equal to L. If you do not actually achieve a certain number L, which does happen, then you would say the series would diverge, and there would be no conclusive answer to what that would be. So let's take a look at this. One family of series are geometric series. It's what we always start off with. And they are a summation of this form. We have a constant coefficient that's a. This constant a does not necessarily even have to be on the inside of the summation. It can actually be outside. So it's optional. You could omit it and just have this r of n minus 1, or you could be more complete and include that. But what you do have is that we have the n equals 1 coming into here, into something akin to r to the nth power, that creates a sequence of what we have here is r times r squared, excuse me, r and then r squared, r cubed, r to fourth, so on. In this first case here, it's missing the r. It's actually there. It's just r to the 0 power, just as this is r to the first power, and continues upwards. And this is what a geometric series looks like. One example could be a positive 1 for a negative 1/2 for r, and as we increase through our counts, we get 1 minus 1/2, plus 1/4, minus 1/8. Notice we got this alternating negative here. Every second term is negative. That's because we got this exponent and the negative is on the inside. We can do that. That's allowable. And with enough times, the denominator will become small, and this will likely converge. In fact, I know it will converge based on stuff that lies ahead. I just know this, and you will too. Right now, you haven't seen how to prove that, but I can just tell you informally, this will actually converge to a number. But that's not always the case. Sometimes they don't, and it just keeps on going up higher and higher and higher every time. And so, what if r is equal to 1? We get an interesting case where we have the first term is a, the second term is a times 1, the third term is a times 1 for when n is equal to 3, the fourth term is a times 1, and you keep on going, and what you end up is this partial sum of a times n. As n approaches infinity, this summation will also approach infinity. So when r equals 1, this sum will diverge to infinity. It will go to an infinite value. So that's one thing to know. There's another case here, and that is when r is less than 1, the limit would be 0. And that means that the summation will converge to a certain number. Let's say L, since that's usually what this book uses for constants that converge. And so here's a little rule they give us. For a geometric series that fits this pattern, if r is less than 1, it converges. And not only does it tell us it converges, it just tells us what it converges to. By filling in for a and r out of this pattern, we actually find out the value, which is pretty cool, pretty remarkable. And in the book, they do have a proof for how this a over a 1 minus r comes about. So if you're looking for a more in-depth study, they do a fine job of describing that. And for r that is greater than or equal to 1, these series will diverge. And that's true of all geometric series. And one other thing I should get into here that's worth mentioning is that for some reason, by the way, this is aligned by such as maybe n is not equal to 1, but maybe n is equal to 2 instead, down here on the bottom, if that's 2. Or to where the first term is missing because of that. Or perhaps n is equal to 1, but instead of an n minus 1, they might just have n, which would do the same thing, cause the first term to be missing. Those are still geometric series, and whether they converge or not, that won't matter. They still have the same kind of convergence, although for it to converge to this value, you would need to make sure all these terms are represented, including the first. And when that's true, you will converge upon the value that you'd find with this formula. But geometric series, if you take a subset of each of these terms that are added, that's still geometric, geometric in nature. In fact, there's equivalent ways to write the same series with different summations. So, keep in mind, such as if you adjust this starting point and this exponent simultaneously, you could end up with an equivalent summation. And that is allowed. That's okay. So let's take a look at our first example. What are the first terms of this series? This is basically just substituting in the numbers. This one starts at n equals 0. And we substitute it in for n. So this is not a geometric series. This is just a regular series. And so we have -1 to the 0 power, -1 to the 0 over 4 to the 0 plus -1 to the first power over 4 to the first. Then we have -1 squared. Probably should put parentheses on here because that's important. Same for this guy too. And that's going to be over 4 to the second. And now I'll do one more term. -1 to the third over 4 to the third. And now there's a thing here, and that is you've probably noticed that -1 squared is a positive 1. And just as -1 to the 0 power is a positive 1. All the even numbers for exponents are going to be positive terms. All the odd number exponents are going to be negative terms. And so this will be an alternating series. That's actually what they're called when they change positive minus. And this is the expansion of that. And the denominator continues from 1, 4, 16, 64, 256, 1024, 4096, 16384, and so on. They just continue upwards. And then they will alternate from positive to minus to positive to minus to positive again. And that's an alternating series. That's what all you have to do is just write these terms. You're not going to need to add them up. That's not expected for right now. Just write them out. Now this here is a geometric series. And does this series converge? You can evaluate these if you want. This is 1/8. 1/8 squared is 1/64. 1/8 cubed is 1/512. 1/8 to the 4th is 1/4096. And 1/5, 1/8 to the 5th power is 1/32,768. And you don't need to actually evaluate these because you could recognize this as a geometric series. And this is the r term in the parentheses, and we have this exponent of n, where n starts at 1, 2, 3, 4. So we have summation of r equals 1 to infinity. And so I had to do a little bit of rewriting because what I had before was n, and this is n minus 1. It differs by a constant of 1. So here this series starts off with 1/8 and 1/8 square. I had to adjust it to make this 1/8 and 1/64 here with this 1 extra in front of it, which was just an accommodation I made. And so I know that what the value this converges to, I'll have to subtract 1 from it. So, but this is a geometric series. Just once we, don't forget we had to put 1 in there, brought this into our correct form. And so we take this, and our A is 1, our R is 1/8. And since R is less than in magnitude of 1, because it's 1/8, the series converges, and it converges to 8/7. And now just don't forget that we've got this, that series assumes this one here, this series. Now this is 1 more, so we'll have to subtract 1 from our final answer. And now it's now this is what the actual previous one would converge to, and so which would be 1/7. And this is one of the more interesting examples, and that is you can take a repeating decimal and write it as a fraction of 2 integers, such as 3.17 or 3.298 or 5.76521, 56721, and so on like that, just where it's continuously repeating. You can actually take any repeating decimal and put it into rational form. And this is the form it takes. Now, 3 is just a necessary evil here. You just include that because it's over here, it's over here. The interesting stuff is the 17 over 100. That's your first term here. That's the first pair of 1 and 7 in this infinite sequence of 1, 7, 1, 7, 1, 7. And if you imagine this being multiplied by 1 plus the 1 over 100 to the first power, 1 over 100 to the second power, and so on. Notice that if you take this to the second power, this is going to be 1 squared over 10,000. So you're going to end up with 17 over 10 thousandths for this term. You're going to end up with 17 over 1,000th. No, 10,000. This is 10,000. And then you have 17 over hundreds. So this is 17 over 17 hundredths, 17 10,000ths, 17 millions. That's the first 3.171717. This is basically can be written as a series of the form of 1 to infinity of 1 over 100 to the n minus 1 power. And in fact, we can make this truly complete and say 1/7 over 100 times this. And so we take this, it's equal to a over 1 minus r, where a is equal to 1 and r is equal to 1 over 100. And so here's basically, let's look at this. Yes, there. So we have a equals 1, r equals 1 over 100. And so this is our form of our equation. This is the a, and then this is our r term. And then you solve this algebraically. This 1 minus 100 is going to be 99 hundredths, which is basically 0.99. And multiply this, you'll get 17 over 99. Well, guess what? 17 over 99 is going to be 17171717 forever. You can add 3 to it and you get 314 over 99 to give you the actual expression of 3.171717. So this ratio of 17 over 99 is what gives that 1717 repeating decimal. This will work for any repeating decimal. If you've got 3 repeating digits, like 175, then you would put 175 up here. You'd have to add an extra 0 in, an extra 0 in, and it'll work. Divergent series, we've been talking about ones that converge. Here's the ones that don't. It's where that this partial sum, the instantaneous sum of the summation you're going as you go towards infinity, outgrows a number L. It outgrows any number L for each additional n term or number of n terms. And that defines a divergent series. So as we take this sigma of n, as n counts from 1 plus 2 plus 3 plus 4 plus 5, does not converge, because if you give me a number n, that's an integer, I'll tell you what this would sum to, and you tell me, and I can make sure I beat it, that I will get a sum that's larger than what the n number you gave me. You tell me a number that you think this would approach, that it would converge to, I will show you an n number that will prove you wrong. So, and any time that you can feel confident to say that, you've got a divergent series. It doesn't mean that the ace of n term gets close to 0. That doesn't mean that it will converge. But if the series converges, then there's no doubt about it that ace of n will approach 0 towards infinity. So a limit is not conclusive to telling if you have convergence. Is not. But you can. But if it does converge, then you better believe that limit will converge to 0. So divergent series, again, this is a test. It's called the nth term test for divergence. You can test for divergence. Can't test for convergence, but you can be certain that a series will diverge. And if you take the limit of the ace of n function inside the summation, and you drive the n towards infinity, if you get a non-existent value, or something that is other than 0, you have divergence. If you get a 0, well, it's inconclusive. Remember on the previous slide I said that sometimes they converge to 0, even if the sum converges. Sometimes it converges to 0 and the sum diverges. So if this limit is equal to 0, it means you just don't know. It could converge, it might not. You'd have to do a different test for the convergence, and we probably won't get to that for another class period or so. But for right now, this will test divergence. A case where you might get a limit that's non-existent, that would be something such as limit as n approaches infinity. And let's do something really mean here. Let's take a sine of n. Well, that would really piss off the sine wave, because it'll start oscillating really, really fast as we get to a larger n. It will do like that, and so that would not have any limit at all, and so that would be inconclusive. Just same way as you visualize a sine, a summation of sine values, on average it will add up to 0. But what if the infinity is a discrete location that you're approaching, that you're at so far, then you might not necessarily be at 0. The average is 0 to a certain value versus like we're comparing expected value and an actual sum, and these are not the same thing. So sine to as n approaches infinity, sine of n is not convergent, nor does the limit exist. It diverges. It won't diverge by much, but it will diverge. And so is this series divergent? Well, certainly, if you take the limit of this, you'll be like, hey, this might be interesting to do. So take the limit as n approaches infinity of 1 over n plus 4. And you get that this is actually going to be equal to 0 because the denominator comes very large. What does it mean if you get a 0? Well, it tells us it's inconclusive because in order for know if it diverges, it would either have to be non-existent or non-zero. So we don't really know for sure if this converges. In fact, I can tell you from just what I know that this series actually diverges. But we can't prove that with this test. So this is inconclusive. You'd have to find out with other means. Is this series divergent? You take this limit as n approaches infinity of n over n plus 10. And as n becomes very large, this is going to be basically into a large number divided by another very equally large number that's just a little bit larger because it's got a plus 10. I'll write that really small because it's going to be insignificant compared to this ratio. This ratio is basically going to be equal to 1, and as n approaches infinity. This is not 0, but it did approach a certain value. It approached to 1, and so this is divergent. We can prove divergence for any case except for 0. And so the limit is not 0. We know for certain that this series will diverge. Combining series you can add or subtract or even multiply by a constant. Not a big deal. But if you and they'll still converge or they'll still diverge. But if you add a divergent series to a convergent series, the sum of those will also diverge. So keep that in mind, because if it converges to a certain value towards infinity, it's just like a constant. If you add that to a divergent series that goes to infinity, of course the sum's going to go to infinity. So if so anytime you add a divergent series, you end up with something that's also divergent. So adding or deleting terms. I showed this earlier in one of our earlier examples. You have we removed a term by changing the you can remove a term by changing the offset, such as setting n equals 2 takes the first term off. It removes a 1, makes this lesser by 1. So in order to make these two, this top and the second series equal, I'd have to add a plus 1 outside the summation. And then these two are equal. And now assuming I'll undo this because I'm going to assume I didn't make that change. The second and third one are equal to each other right now. They have a different starting point. The lower one starts off at n equals 1, and the upper one starts off at n equals 2. They're equivalent in the sense that I also adjusted the exponent, n minus 1 versus n. You'll get the same values summed up. They'll always be the same. They will both have the same convergence or divergence properties. So sometimes it is convenient. Personally, I like the lower one better. It looks cleaner because you don't have a minus 1 in exponent. And if you want to make something that's easier to read, it's good to know that. If you're using Wolfram Alpha and you're needing to do a series expansion, Wolfram Alpha does a terrible job of giving you a readable series. And if you want to make something look nice, you will almost certainly have to do this. And some of the stuff towards the end of chapter 10, you might be needing to do. You'll certainly need to do some of that in Calc 3, where you need to go to Wolfram Alpha and maybe to check your work. But in order to check your work, you'd have to make adjustments, because they very well can end up with something such as an n minus 2 in the exponent, and you would need to adjust to your starting point to make the exponent nice. Such happens with computational machinery. And that process is called Rei Indexing too, where you adjust your starting value and your exponent to make them more readable. Like I said, this is easier to read than this. In fact, starting off at n equals 2 is almost a dirty trick, because people usually expect these to start off at 1 or 2. At 1 or 0. Starting off at 2 is a little bit weird, so not very common. But they're equivalent. They do the same thing. They're the same sum, same series. So they're both geometric series with r equals 1/2. So anyway, that's our introduction to series. Our next one up is we're going to do the integral test. These are a couple more tests we're going to do for our series, if they converge or not. We're going to actually talk about harmonic series, which are related to this. It's a different type of series. We'll tell you when they converge or diverge. So I'll see you then.